Okay, let's get started. Welcome to, this is our 5th lecture of the pre-course, Interactive Mathematics with Mathematica. Okay. Now, as I've said probably once or twice already, the purpose of this course is a little bit of, is twofold. One is to make sure that the incoming class of Basai students are equally prepared in terms of the mathematical background coming into to college, because some of you, did a lot of maybe high school calculus, linear algebra, but some of you absolutely didn't. The other purpose is to get you introduced and start practicing on the Mathematica programming platform, okay? And the purpose of that is also twofold. One is that it gives you the foundation for what's called functional programming. That's the mode of programming that I guess most of you will have to be familiar with at some point. Some of you would actually go on to spend a lot of time picking up another language like Python, or maybe JavaScript or R or something like that. And Python accommodates a few paradigms as well, just the same as Mathematica, but mostly it is a functional programming language. What it means is that the way you ask for the computer to do things for you is to not give it instruction, but to sort of like prep it with a library of function. And whenever you want something done, you just call on that function. And so when you build that up into an algorithm, it's like a sequence or a logical calling of different functions. Okay, so think of function as a little bit of execution, and you string them up together into like a recipe for the whole algorithm. Okay, and the reason that this Mathematica is going to be useful is, first of all, it's a very powerful language. It has a lot of built-in functionalities from engineering to scientific computing, not to mention machine learning and whatnot. But also because for those of you who are going to be looking to have a platform for expressing your ideas or prototyping your quote unquote little apps. Okay, you want to come up with some kind of an app that does this or that. The easiest way to do that is to actually prototype it with some high-level language, high-level tools like Mathematica. Okay, so anyway, today we actually we've gone over some basic foundation of what it means to do mathematics, the algebra, the linear algebra. And today we're actually going to sort of like pivot from linear algebra to calculus. Okay, so we'll cover a bit of calculus probably in the second half of this class. Right, but first let's go over what I call the useful list. Okay, so like I said, Mathematica has thousands, maybe 10,000 by now built-in functionalities, but these are the ones that I think you would find most useful to know. It's sort of like a starting kit, so to speak. Right, so I'm gonna start off with essential tools. These are kind of like things that I have compiled into a short list of what you have in your toolkit, in your bag of tools, right? All of these can be expanded. There are versions, there are more elaborate functionalities built around this. So whenever you see some of this function, it's not exactly what you want to do, it's not powerful enough, you can always go to that function and just enter F1, right? Type in F1. It's going to take you to the reference page. It's going to give you related function. But these are sort of like a bare minimum, so to speak. Okay, so we talk about language primitive. I'm going to go over quickly because we actually did use some of this already in previous class, right? So the most primitive thing you need to know is equality operator. Again, This is not a logical equality. This is not an apple as good as a banana. No, it's literally an assignment. So it's assignment. It's saying x is equal to 1. From now on, x that used to be this little blue thing, right? The computer doesn't know what it is. It knows what equality is. It knows what 1 is. Okay, so this is equality operator. So it's all in black. This one is in blue because it doesn't know. Okay, so once you shift enter, it knows that x is now equal to 1. So until you tell it otherwise, this thing is globally known as 1. Okay, now something that might be different with other language is when I actually start a different file, different application, this x is also known over there as well. So I can literally create a new file, new program. But once I've done this kind of in my session, so it's known globally per session. Okay, so obviously a useful thing that I show you before, somewhere down here, is to somehow encapsulate the meaning of x. So I don't want it to be known all over the world, everywhere. So I put it under things like module. Okay, but anyway, so that's the most primitive, right? Second thing you need to know is a list, right? And we talk about this. Now, list is so generic. I can literally do this. My silly little list is a list of this thing. Okay, it's got all kind of stuff. So I shift enter. Actually, I should do this first. Let's delete all output. Okay, so if I do this, it's a list, right? And so this is actually, I can enter it manually. Okay, so it can put a whole bunch of things together: symbolic, text, color. It doesn't matter. Okay, so that's sort of like arbitrary thing. Now notice pi is actually a real, I guess, universal constant, right? In fact, if you ran into an alien and you know what numerical base it does, let's say you look at the alien and it turns out the alien has 10 fingers, you can assume that the alien used a base 10 number and you can communicate 3.14. And that's how you tell an alien you are intelligent enough to have derived at the universal constant of pi or something like that. But anyway, it's universal constant. So unless you tell Mathematica you want the numerical approximation thereof, it's going to give you as pi. Okay, so this is not exactly pi. Anyway, so now once you have a list, oh, this a little built-in function. So I'm going to give this to you in the line group so you can play with it. It's most of it is self-explanatory. So I'm just going to keep on clicking, right? It's a function that beeps. Unfortunately, I haven't turned on the computer speaker. Otherwise, it would just beep. You can also ask it to play piano key or whatever, and so on and stuff. Blah, blah, blah. Okay, this little semicolon, once again, is a way of suppressing the output of the previous command. Okay, fine. Put all this in the list, blah, blah, blah. Now, this is equality in the sense of logical equality. So you can do this, right? Is A plus B equal to B plus A? It turns out to be true. Logically, there are 3 things here I'm doing. Okay, F1, F2, and F3. I can use this functional notation, and this is the one you would see the most in Mathematica and also in Python. Okay, except in Python, it uses a soft circular bracket. Okay, so this is saying take X, do F1 to it. Once you do F1 to it, you do F2 to it. Once you do F2 to the outcome of that, you do F3. So it's a compound function. Again, this is a notion of functional programming, but there's also a shorthand for it. Sometimes because, you don't want all this kind of bracket to stack up. Sometimes you just say, okay, apply F1 to X, then apply F2 to that, then apply F3 to that. So this is kind of a pre-applied notation. Okay? It means exactly the same thing, but sometimes it's more handy. Sometimes it's more handy. Okay. Another one is a shorthand, except instead of pre-applying, you post-apply. Give me an X, do F1 to it. Whatever I get from there, I do F2 to it. Whatever you get from there, you do F3 to it. So these 3 are exactly the same thing. See? Checks out through. Okay. But this is kind of like an assembly. Give me an X, do something, then do something, then do something, then do something. Okay. So this is the proper mathematical functional programming notation. This is kind of shorthand for pre-applying. This is kind of shorthand for post-applying. Notice that I put a little bracket here because if I didn't do this, sometimes the post-applying would kind of like draw its own bracket and not exactly what you want. Okay, so this is also special character, Euler's E, right? Euler's very famous mathematician. Some of the special character, like I told you, if you don't know how to refer to it, you just go to palette and go to special character. But I happen to memorize, for example, escape. Oops, where am I? Escape. Okay, INF, escape. That's infinity. For example, escape. Euler's expect, so some of these I just use so often, like pi, infinity. Right. So this clear all. This is because if you haven't made the modular assignment, like a localized the value, X is now known universally until you turn off the machine or the program. So now I cleared everything. So it becomes a blue object again. So now it doesn't know what X is. Anyway, this is something called random seed. You find out about this later. This is very useful in modeling, in computer simulation. Okay, table. Okay, table is one of the most useful way of creating a list. It's creating a list, but not any kind of list. It's a list with some kind of logic. And that logic is driven by the index. So I want to say list of 10 things. And the position, I want the value to be equal to the position square. So that would be the table of I square, I going from 1 to 10. Okay, so we did that. Random integer, this is really very high language use. If you were to do this in, say, C++ or something, you have to maybe initialize some randomness and so forth. But it's very easy. So I'm just going to skip over that. Now, the list is an unstructured list set, just a list of things. It doesn't actually really have any kind of mathematical property to it. But in our case, the one we use a lot, we use the most is to do simple multiplication, addition, but not to a single number. We want to do to a whole bunch of number at once. Okay. In particular, those whole bunch of number may represent a position in space. So in which case, I would refer to 3 numbers together as a 3-dimensional coordinate, right? In linear algebra, which we talked about, the previous 2 class, that would be known as a vector. Okay. So even though this used exactly the same syntax as the silly thing that I wrote before, by applying it to some number, it becomes a vector of number. Okay. It could also be a vector of imaginary number, but we're going to work with just a number. So all this, basic stuff. Okay. Now, the shorthand that is useful, again, this is not particularly logical, but the reason I put it here is because it's so very useful. Okay. Just as you can apply some function to something, you can apply a function and say, let's apply to all the things in this list. So instead of using application, right? So if I have something like a pi, okay, and I have something like 3/2, right? And I want to say, okay, I want a numerical value of this, so I can do that. I also want a numerical value of this, okay? So I get that, right? But let's say they don't come individually; they come in a list, like this, pi, and 3/2, right? Comma, right? I want to apply, but I don't want to apply to the list. I want to apply to individual part of the list. Okay. ไม่กินน้ำเปล่าอ่ะไม่กินน้ำอ่ะทานน้ำหน่อยลูกแม่เป็นห่วง right, so this is applying, but it's applying to this guy and it's also applying to this guy and as many as there are, so you get that. Okay, so this is, again, I put it here not because you need it as part of because it's a formal language, but it's a very useful shorthand. Now, this another thing that is very useful. Multiplication is just an empty space, right? A multiplied by B, you just say A blank B, okay? Likewise, if I have X and Y, okay, in this case, these two things, this list, what do you think is going to happen? Now, we talk about the dot product, right? That's sort of like one is a vector standing up, one's a vector lying down. You take the first one, multiply, then you add to the second pair, multiply, add to the third pair. But if I did this, what do you think happens? It's actually going to recognize this as, well, in a way, it's kind of common sense. What would you like to do? You like to multiply two things. Two things happen to be a list, but you haven't specified that you're doing something specialized in mathematics like dot product. So what it's going to try to do is to say, okay, maybe you want to do item by item or element wise. That's another word, element wise multiplication. So that's it. That's what it does. 2A, right? But it's not adding them together because you haven't defined yet. That's what you want to do. Now, what you want to do in dot product would be this dot, right? And now you get 2A plus 5B plus 10C. So we got this. So this is some review. So this dot product is from last class. So anyway, so all this primitive. We also talk about user-defined function. We talk about two cases. One is when you name it. Okay, so this is like a built-in function, but it's doing something that the machine, you know, once you say bought the software, it's already there. But if you wanted to do something specialized, you have to name it. You have to create a new function. So this name function here, this is a built-in, right? So it's a sine function. This is a plot of a sine function, or this is actually two different functions. This is a sine function, right? This is a trigonometric. This is to say plot this thing, X going from minus pi to plus pi. So that's why you get this picture, right? Now, so this is a built-in, but you want to do something more special, okay? You want something like my sine plot. So instead of leaving this specified, you want to say, I want to say what my left bound is, what my right bound is. So my sine plot, and I give it generic A, I give it generic B, it's the same thing as plot sine X, X going from A to B, right? In which case you can do anything. So this is another one. This is your own, right? So now instead of having to do this, you can just say, you know, my sine plot, whatever, minus 12 to 33 pi or whatever, okay, right? Inherently, that's the same thing as doing this and put minus 12 and 34 over here, okay? So why would you do that? Well, because that's exactly what programming is about, okay? A programming, first of all, that's the difference between a calculator and a program. Okay, if you use Mathematica as a calculator, you do something like this. Give me a calculation of sine pi. But as a programming, you don't want just that. You don't want to just give it pi and get some result. You want to do something to it. So you string together a whole bunch of built-in functions. But not only that, once you strung a whole bunch of built-in functions, you don't want to keep doing that again. If this is something you want to do all the time, you name it. You name it. So it becomes your mini recipe. So always think of functional programming as creating recipes and recipes upon recipe upon recipe. And at the very high level of recipe, you can tell that I want a dinner party. This dinner party will consist of a souffle and, I don't know, roast beef, okay? And that function called souffle would call some other function, right? All the way down to, you know, roast beef, all the way down to maybe slaughter a cow, I don't know. Okay, the point is at the very top language, mathematics is a very high level language. So there's a lot of built-in recipe, okay? So you can come in and say, I want a souffle, and there's already a default function for souffle. Now the trick, the key part of using Mathematica, and this is the power, okay? Not only can you string function together, you will realize that this function, this simple built-in function, okay, whatever that built-in function is, it also has many versions. Some version just takes one parameter, like, okay, this sign, okay? In this case, yeah. Okay? But if you do this, just go F1, okay? Oops. Yeah, it's gonna go to to special. Okay, in this case, well, sign so says only has one function, one value. Now, what if I do something like plot? Let's look at number plot. Okay, plot function, right? Just take something between here and there. Instead of just using it naively like this, you go press F1. It actually gives you various way of specifying. So this is like souffle, but you can maybe apply special little instruction. So maybe plot this from here to here, maybe plot a whole bunch of them. Maybe you plot this up to some kind of region. So there's kind of like, and then there's like all kinds of arguments. So this would be options. Okay. So to wrap up, and this is where you want to take this all the way to, you know, any other language, JavaScript or whatever, Python or whatever, you have built-in function. That function takes argument. A good design would be, it takes the most basic, just one argument to do something, because it assumes the rest. It assumes the rest as default. Okay. So there's always this thing called function, argument, and default setting. Default setting is what makes the program really cool. Okay. So it's a little bit, and this is where this differs a little bit from mathematics. Mathematics, when you say assign function takes one argument, it always takes one argument. Okay. When you have a function, it takes two arguments. Maybe sometimes it takes a list. Okay. But that's it. You just have that version of it. Addition takes left and right. Okay. If you want to take more than two things, you have to recursively apply it. Well, with programming, they kind of assume that you give the function add or plus, and you give it three things. What you want is really to add all three things together. So it does mathematically 2, A plus B, and then take the result and then add to C. Okay. So that's, so right away in functional programming or anything you do for the rest of your BASI curriculum, when you use functional programming, Mathematica, Python, JavaScript, I don't know, chances are the built-in function will come in a variety of setting. Okay. And at the minimum, this function expects one argument, you give it. But sometimes it gives you other option. Okay. If you don't specify the option, that language, whatever it is, will invariably use what's called default setting. Okay. So this is where programming is a little bit more handy than mathematics. With mathematics, you have to be precise, right? Addition only take 2 arguments. But here, addition can take 5 arguments because it assumes that, yeah, what you really want to do is keep adding until you get all of them, right? That kind of thing. Same thing, function like an average, right? If you define it mathematically, you take all the elements, add them together and divide by the number of elements. But if you notice, like in Excel, right? You have number 7, number 8, number 9, and then you have the word apple. And you want to take an average. It kind of knows that you cannot really average apple with 7, 8, 9. So it's actually going to give you 7, 8, 9 divided by 3. Okay? Because it knows that apple cannot be average. So computer programming is a little bit easier to use than mathematics, okay? Because it allows a little bit of common sense. So that's what you get that a lot. So high level language like Mathematica will apply a lot of common sense thinking. This is sort of like an example. I think I used this example last time. This is my own definition of Pythagorean theorem. Okay, so that's obviously take the first thing, square it, add the second thing, blah, blah, blah. So now pure function is a bit like this, except it's a monkey see, monkey do kind of thing. So instead of defining something you want done with A and B, you just say, I want to do this to 2 things, then immediately apply to A and B. Why is that useful? Because it doesn't clutter up your program. Because once in a while, you know, I just want to do things once, like put this on top of that, right? I don't want to create a function that's globally going to put 2 things together. I just want to do this one. So I say put this on top of that, apply to object A and B, and I'm done. So it's a pure function. That's also very handy. Okay, so I'm gonna now. So you got the primitive, you got the function. Okay, so think of primitive in the first one as basic, very basic thing, using it as a calculator almost. And function definition, now you're talking about a language, it's trying to get to do something, right? And oops, sorry, I went a little bit too far. No, okay. So this kind of like built tensor, we'll talk about that. So user defined. Now, the thing that's useful, again, because a lot of you are not going to apply digital intelligence, but you're actually going to smart cities, you're going to sustainability challenges, you're going to healthcare. Some of the time you want to show something, okay? And that showing something, well, mathematically, it's plot, okay? So plotting function is very useful. And remember what I told you? At bare minimum, you can give it bare minimum. Plot what? From where to where? Okay, so that's like what we called earlier, but everything else is default setting, right? The size of this, right? The marking, the axis, marking it as 1, 2, using this color blue, all this, you don't have to say anything. This is sort of like a default setting. But if you want to be fancy or you want to customize, obviously you can specify all kinds of stuff. So for example, I can do this, right? So I can specify the color, I can add the name to it. So this is saying the style is to make it thick with color blue and have to give it a label and blah, blah, blah. So you will see that some of my codes that I was actually showing you last time looks really long, right? But it's not long in the Python sense. Python, the code is long because sometimes you have to keep writing what's called boilerplate. That's sort of like a standard code that you have to keep writing because you want to do something. It's not high level. Well, this thing is high level, so I can do this in one line. Okay, but if you are fussy, you're fussy about the formatting, the appearance. This is where you can get a lot of, you know, very cluttered looking codes. Now, I have to admit that this doesn't look very nice, but why do I put up with it? Because, you know, it allows me to do something pretty, okay? Just make colors nice and blah, 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 okay? So you see a lot of my code that I give you as an example, especially in my data analytics. It's, you know, maybe like 20 lines long. I can tell you that 15 lines has to do with formatting, making things look nice. Okay. So again, so this is a built-in again at the minimum. See, you don't have to do anything else, right? It plots 3D. Now, I can, as an exercise, if we have a lot of time, I say, tell me what are the defaults in here? There's a lot of defaults in here. First of all, I'm plotting things in yellow. I don't have to plot it in yellow, so that's a default, right? Second of all, perspective. I'm looking at it from this view. How come I'm not looking at it from that view? That's also default, okay? But if you want to play with it, you immediately have an application. And the minute you want to show your client, you want to show this picture. You can set that. You can set that in terms of perspective, okay? So how would you see that? You go to plot 3D, F1, and this is all in here. So you want different colors, different, I don't know. So look under options, okay? Background, axis, background, boundary style. I don't know. I don't really care. Okay. Color function, right? Try different colors. Okay. Again, so this is why you get a lot of you know, very many lines of code because you want to be fussy about details. Oh, I want dark rainbow. Okay. I happen to like dark rainbow. I like this. I like kind of like a, okay. All kind of things. Filling, fill style, and so forth. So this is why, this is the difference between, you know, mathematical function and computing function. Computing function allows you not only the bare minimum that the function expect, but also, if you want, add options. Okay, this is how they built into the flexibility of the language. This is not the most fundamental part of functional programming, but it's the most convenient, right? Because if you think about it, let's say this is year one, Mathematica came up with this, okay? And then somebody say, oh, I like the plot, but I really want to paint in different colors. Can I specify different colors? So, they add options, okay? So that's why functional programming is a bit like that, okay? This is, so because you're not building things from scratch, you're using the built-in function. The difficult part, or not the difficult part, but the tedious part is you have to read the manual, okay? So it allows you to plot in red, in blue, in orange, in big plot, small plot, high. But the point is, because you're not doing it yourself, you're using it by specifying option. You have to read the option list. Okay, so it's a little bit like that, right? So if you buy a car, you have two options, right? In the old days, you buy a car. If you want different color, you paint it yourself. Okay, that's difficult. So they make life easier, but it's still not perfectly customizable. Cars only come in 5 colors, blue, orange, yellow, and black. So when you buy it, you have to specify the option. That's what it means, okay? So just as when you buy a car, you have to read through the option list. When you use a function, again, this applies to Mathematica, Python library, everything. What you have to do is, I want to do this, but I have a special requirement, special request. So request is red, it's black, size is big, and so forth. So you do all kind of stuff. So this is, this can take you forever to specify something to exactly the style you want. But it's not the most important thing, okay? You can literally communicate your idea across to your, prospective investor, whatever, with built-in function. But of course, if you have a lot more, fancy thing about, I want to show this line in red, blue, and the client can specify whether or not they want to use the color red, you can build that in. Okay. Now, so this is kind of like optionalities that you can play with, right? But this is your optionality. You specify the option. Let's elevate this to the more like a user end. That's where Mathematica's manipulate function becomes the most useful. So all these things that you could play with yourself, because you're reading through the option list, right? I can paint in black, blue, green, yellow, big, small, whatever. Well, what if I want to make it like an app? Then I allow all this formatting to be subject to the client. So this would be something like this, okay? So now, except formatting is rather trivial, right? Colors and blah, blah, blah. Mathematically, you can specify all kinds of stuff. So this is where manipulate comes in, okay? So things that was your option to begin with, right? It's your parameter. Instead of just specifying yourself, you make it an option. So this is really, okay, let me put it this way. The language of functional programming gives you built-in function, okay? And when you write your own function, you're going to mimic the style. So my comments here apply to user-defined function. The thing is going to give you a function to do something, but it also gives you options to specify nitty-gritty details yourself as a programmer. But if you are the programmer, you want that optionalities to be exercised, to be explored by your client, right? I can draw you this picture. You can paint a house. You can paint it in red, blue, and green. Yeah, you can do it yourself. But if you want to sell it to a house buyer who's not a programmer, you would sell a program that draws a house. And then say, all these optionalities, I'm going to put it as a button, give a user interface. So instead of using the function yourself to say blue, red, green, big, large, small, this angle, that angle, from pi to minus pi, 2 pi, 3 pi, you make all those things into manipulate. Okay, so you cover that with manipulate, and things that you want your prospective client, your whatever, your user to play with, you put it in another thing. So this is a range. So I happen to have this range from 1 to 10. So this gives you a higher or lower frequency. Okay. I'm actually doing this for my own project that I'm, selling to asset management advisory kind of work. Okay, so client can have different criteria about risk and return. Well, obviously those are parameters, right? I can program the computer to optimize for this risk profile, that profile, but instead of just doing it myself and just ask prospective investor, I can literally have this app for the prospective investor to actually play with their own risk profile. Okay, so this is something I would do. In fact, I'm doing. Yeah, and again, this is formatting, right? So I can do kind of different kind of stuff. Doesn't matter. Okay. I can put the placement to the right. I can put my name on it. So if this is a software that you want to patent, you might write your name down and say that you're applying this for patent number so and so. Okay, so somebody can look at it, play with it, but can't infringe on it. Okay, because it's your thing, right? So now I play with a whole bunch of things. I can whatever. Okay. So this is a little button style. Okay, this is a little button style and so forth. So what we got so far, we got the most primitive, as if you were using a calculator. As per functional protocol, functional programming protocol, you have this concept of function, and function is how you communicate computer to do something. Okay, that requires many steps. The useful functions are, well, first of all, because you want to be visual about this, and this is very much the ethos of design thinking and visualization that comes with Basai curricula. Plotting and visualization is going to be a big function. Okay. Now, this is, by the way, this is one of those things where in Mathematica, even though, it looks a lot tedious, right? You have to specify this. I guarantee you it's a lot easier than if you were to do this in Python. Okay. In Python, you have this thing called matplotlib, and it's very difficult to use. Okay. So this is, they have Seaborn, bokeh, some programming on top of that, but still it's not that easy to use. So this is, even though you look like, oh, this looks like a lot of, tedious specification of colors, name, it can get a lot more tedious if you were to do it in, say, matplotlib. Okay. To do this in matplotlib, I guarantee you can ask my TA. It's going to take more than at least 20 lines probably to draw this picture. Okay. Whereas this is actually one line. Although, good. And so that's plotting. Interactive plotting, this is where the name, the interactive mathematics come in, is by using a lot of this manipulate. Okay, fine. Now, these two things I'm going to come back to, because differentiation and integration is when we pivot to calculus. Likewise, in optimization, data handling, I might not even cover that, except I want to show you that there's a lot of built-in data repository. Okay, when I have students do something like machine learning in Python, let's say, I would ask them to go to GitHub or go to Kaggle. Kaggle is also a very good data repository for competition, but you also have a lot of data library built in. Okay, so these are sample data. Okay, I just happen to pick up something silly like cabbage, property of cabbage or something. I don't know. Let's see what happens. Huh? Oh, so they mention all kind of stuff, observation, source, time series. So apparently there's a time series for cabbage, probably price of cabbage or something. So this is not part of the core language, but it's part of the sort of like a service. So when you have the software, you have login and you can access that. What is this? Yeah, I'm not going to cover this. So this is something that I would be covering quite a bit in data analytics. Okay. So let's go to this solving equation. Well, let me shift gear and go to this page. And this is where, we're going to do the final coverage of linear algebra. Right. I told you guys that linear algebra, right? It's like algebra, just doing adding, multiplication, and so forth. So you're not doing like exponential you know, that sort of thing. You're not doing sine, cosine, trigonometric. You're just doing multiplication, addition. Okay. Now, it turns out that you can do this for a vector of any dimension. And we have that specific rule, right? The dot product has to be the row vector of length n can multiply a dot product with the column vector of length n. So that dimension has to match. Likewise, you have two matrices that can multiply. You have m by 75 multiplied by 75 by n. M and n can be anything. As long as the 75 match, you can multiply them together. Right? Having said that, the most useful, well, not the most useful, the most ubiquitous case is when you are multiplying a vector by a square matrix. And why is that? Because if you multiply a vector of dimension k by a k by k matrix, the result is going to be another vector of dimension k, right? And why is this useful? Well, it's useful for all kinds of things. And the example I like to give for your generation would be a game programming, right? Game programming, I have to sort of like model in 3D space or maybe 2D space. But let's say in 3D space, how do I manipulate movement in 3D space? Now, movement is not just movement of the thing in the 3D space, movement of your perspective. So the thing hasn't moved, but you move your perspective. That's also movement, right? Well, all this is done by multiplying a three-dimensional vector, x, y, z, x, y, z, multiplied by a 3 by 3 rotation and extension. And well, that's computer graphic, right? Well, that's sort of like take this, multiply, and then get that. Well, there's also a reverse question. What if you get the output? What is the input? And that goes back to what you did when you were in grade school, which is to solve two equations into unknown. Okay, two equations into unknown is like saying you have a two-dimensional output vector y. You knew that this came from A, which is 2 by 2, multiplied by two-dimensional vector x, x1, x2, and you want to solve backward. Okay, so this is the opposite of what you're doing in computer graphic, right? Computer graphic, you start with a location, 2 or 3 dimension, multiply by square matrix, you end up somewhere else. Well, when you solve system of equation, you got something else. You got the result. You want to find out what got you here. Y is equal to something x1 plus y1 is equal to something x1 plus something x2. Y2 is equal to something x1 plus something x2. And you want to reverse that process. Well, you write it as y is equal to matrix A, which is 2 by 2, and then x1, x2. And then you find the reverse of that. So that's, you know, so that's why you get this. But notice, and this is, I'm being interesting here. You can do this when you could have done this when you were in 5th grade, right? You did this in your 5th grade. But I did this analytically in Mathematica using function solve. Okay, now obviously it's one of those riding an elephant to catch a bug thing, because this same function can be used in Mathematica to solve very difficult non-linear algebra equations, and you would do that in calculus actually. Okay, so anyway, I'm just doing kind of solving, but I think we went over something like this last time, which is to say that if I have two equations and two unknown, if I solve them separately, it's kind of circular, right? You get x1, but you get x1 in terms of x2. You also get x2, but you also get x2 in terms of x1. So what? Okay, so you have to solve them simultaneously, and that's why you do this thing. Okay, and then you get the solution. And this is how I show it, and blah, blah, blah. I can do this in 3-dimensional as well. Okay, and you guys remember, if you have two equations and two unknown, what can happen? There's a 3 situation in life. This is what I want you to remember. You have 3 situations in life. You have unique solution, you're done. The other 2 cases are trickier. Either you have no solution or you have infinitely many solutions, right? You have one solution because 2 lines cross. In higher dimension, just move up 1 more dimension. you have 3 planes that cut across and you get a point. So that's that point. Okay. The other situation is they just happen to be on top of one another, right? So 2 lines on top of another, you have infinitely many solutions. On the other hand, you can also have no solution because you have parallel line never cross. Okay. So you have the same thing here. So play around with this. Okay. If I give you this, you can play around. Basically, these are the coefficient. If I make the coefficient equal, then something would be messy. Okay? And that's it. So dot product, matrix multiplication, these are all the fun games that I built in. This is going to be eventually a textbook, but sort of like an interactive textbook. Now, before I leave, I give you final special case. Okay, like I said, you can multiply any matrix m by k to k by n. But the most usual case you have is n by n multiplied by n by 1, which is a vector. And that gives rise to something that's more powerful than you thought, which is what's called eigenvalue or eigensystem analysis. What it means is that when you multiply a point in 3D space by a square matrix, a 3 by 3, what you do is you kind of rotate it and you stretch or shrink, or maybe it goes, negative. And that sort of like means it's not stable. It's sort of like it's not boosting itself, it's not giving a good feedback. But if you think of some particular peculiar direction that you multiply by the square matrix and it just keeps going in the same direction, except bigger or maybe except smaller. Okay, so keeping to the same direction, the German word for same is eigen. A pair of matrix and vector that somehow when you multiply, you get something that just same direction is called eigensystem. And on Friday, I think was I had a talk, an introduction to applied digital intelligence, and somebody was asking me, I think a student, a girl was asking me about, why Google beats everything and became, world dominant. And I gave a detailed explanation that the reason that Google conquered the world right now, I guess, is that they weren't just programming web search. They were applying an algorithm based on eigenvector or eigensystem analysis. Okay, details, we'll talk about that. I'm not going to talk about it here. Instead, I'm actually going to just show you. So this is this is sort of like a multiplying, right? So this is, you start with some x. When you multiply by square matrix, it changes direction. It kind of rotates and it stretches and shrinks. Fine. Okay. But if I did this, and you can't see it very much, but see, this is the purple and orange. This is what I mean by eigenvector. It's starting somewhere. It's going to get longer or shorter. That's it. Okay. That's it. Good. Okay. So I think, yeah, we can play with this. Now, let's pivot to calculus. Okay. So everybody with me so far? Okay. Well, let's do this. Let's do this. Okay. Let's do this. Let's say, I'm going to say this, okay? I'm just going to make this up, okay? Let's make this up as I go along, okay? F of x is equal to 60. Okay? I just did this, okay? Just for some weird reason. Okay? Weird reason. Okay? Now, okay? Now, I say, and I'm going to do something else, right? I'm going to say this is 60, f is 60. So I can plot this, right? f of x, x going from 0 to 2. Oops, sorry, x going from 0 to 2. Okay, that's it. It's a very boring function. It's a very boring function, right? Very boring function. Now, what if I told you that, well, instead of x, let's make it f of t. Okay, f of t. Okay. Well, I haven't put any label, so it doesn't really matter. It's the same line, right? Now I told you, now I'm telling you, f of t is the speed. Okay, so I'm just gonna make a note in text. F of t, in English I can use a curly bracket, is equal speed of your car at time t, right? So what I'm doing this is the first half an hour, 1 hour, 1 hour and a half, 2 hours. You're driving at a constant speed. It's very boring. Okay, so anybody wants to tell me the distance? Well, I'm gonna do this. My distance, I'm gonna call it big F. Big F of t is equal to 60 t. That makes sense, right? Because the distance that I accumulate, assuming I start from 0. Now, don't ask me how I can just start a car, immediately go 60 miles an hour. Okay, but I can do that, right? Right? I can do that. So now I want to plot them together. Again, I can do this, right? I can plot f of t together. Right? So there. Okay. So let's do this. Plot label, right? Plot label. What's the first one? Speed, comma, distance, okay, versus time. You can do this. You can literally, yeah. I mean, you have the computer, you can key this in, right? Okay. Now, what if, you notice the speed is constant? What is this distance? I'm just multiplying, right? So all I'm doing is multiplying and I keep adding, right? So by the time I get to 2 hours, I get 120 miles. That makes sense, right? Yeah. Okay. So if I did this, speed, f of t, accumulate distance up to time t, accumulative distance travel by your car. Okay, right? Anybody else can think of anything else that has this kind of rate? Rate. Okay, I'm gonna put star. This is something about rate. Okay, and this is some kind of accumulation. Anybody else can think of any other situation in life where you have rate and accumulation? Download something. Yeah, exactly. Exactly. You can have rate of, bits, megabyte per second, right? And how many seconds, right? You accumulate everything in life that has time in it. Chances are you're going to have this. What else has time? When you put your money in a bank, if you put your money in the bank and you take it out, nothing happens. But if you put your money in your bank, you give it time. Anytime you have time and you have some kind of action, what's the action? What happens when you put things in the bank? It kind of like grows, some mysterious reason. You don't have to know why, but you put your money 100 baht in a bank today, you give it time, comes back, it gets bigger, right? You put a plant, it's about a foot tall, you give it 2 months, it gets bigger, right? Well, think about it. What's more natural to you, the rate or the result? Chances are you actually look at result first, right? Right? So I'm going to put it the other way around. What if I told you first? What if I told you first, not the speed of your car? Okay, I haven't shown you the speed of the car, but I show you the distance you travel up to that time. Can I do that? Yes, I can, right? So I give you the big F first, and then I give you the small f later. That makes sense, right? So somebody's driving from here. Okay, this person is here. 2 hours later, where is he or she? He or she is over there. What is the speed? It is total distance divided by time, right? So if you think about it, is there a relationship of that thing in here? Well, yeah. If you take the slope of this yellow line, okay, how tall is it? 120. Okay. And this is dead easy. This is common sense, right? I'm almost insulting your intelligence here. Right here, what's this point? 120 and 2. You have 120, you divide by 2, what do you get? What do you get? You get 60. Right? So it's actually measuring the rate of change. Now, I told you guys you're familiar with driving a car, so I start with the rate of change first and I get the distance. But actually, let's flip things around. Start with the distance and get the rate of change. Can you do that? Yes, you can. Yes, you can. Now, here's where it gets more interesting. What if you only knew that the person is over here at time 0 and 120 miles away in 2 hours time? But that person is not traveling at a constant speed. What do you know? You can tell, this is common sense, right? At some point, he is driving faster than 60 miles an hour. At some point, he's traveling slower than 60 miles an hour. At some point, you just know, okay? Because he's not at a constant speed. If he's at a constant speed, he's at 60. But if he's not at a constant speed, he can't be below 60 all the time because he wouldn't get there. If he's traveling at other speed, always higher than 60, at some point, at no point is he traveling at 60 miles an hour. He's going to be way too far. So you know that at some point he's faster, at some point he's slower. And let's say your car is not a magic spaceship, so it kind of has to speed up gradually. At some point, the car is going to be traveling at exactly 60 miles an hour. That's called mean value theorem, but never mind. The point is, you can do this, right? You can do this in your head. Okay? You can do this in your head. The point is, what if you want a smaller amount of time? In other words, you start with yellow. You start with yellow. And you want blue. Okay. Now, I'm going to show you something. I'm going to show you something. Watch this. I'm going to flip this around. I'm going to put F first. F first. Right? Watch. And little f, I'm not going to put 60. I'm going to make life difficult for myself. I'm going to put D, open bracket, F of T, comma, T. Okay? Okay? So let's see what happened. I'm just going to write this out. Okay? Right? And I put in some number. Oops, it doesn't. Never mind. This thing is, wait. There's a technical reason why. Yeah. Let me make sure that I consult the format. Yeah, okay. Okay, so instead of doing this, I know what I did wrong. And I had to put my glasses for that. This is actually the same F. Sorry, what I meant is this. Okay. Typo. Okay, so this is what I meant. Okay. Let's see if I get this. Okay, good. So it's the same as before. It's the same as before. Don't ask me why I take this little colon out, but you know, just there's a technical tiny reason for it. Anyway, the point is this thing here is a built-in function that gives you the slope. Okay, I haven't told you what it is. It's shorthand for something. It's a function called D, and this function gives you the slope of this function over this, which is easy, right? You can do it in your head, right? What's the slope of this line? 120 divided by 2. Okay. Now, what's so nice about this line, this orange line? Let's say I make this graph too big and I can't see it. I just hide part of it. Can you still do the same calculation? Can you? Yes, you can, because you don't have to wait to 120 divided by 2. You can just look at this and you say, oh, it's 40 divided by what? Divide by 0.666666. Or it's equal to 30 divided by 0.5. Because this is a straight line, the slope is constant. Okay, so my life is easy, right? You can do this in your head. You can take 120 divided by 2. You can take 60 divided by 1. You can take 30 divided by 0.5. You can take 90 divided by 1.5. You get the same number, right? Because the guy is traveling at a constant speed. So the average speed is the same thing as the speed everywhere. So now imagine, okay? So now imagine, let's do this. Okay. Okay. Now what happened? Oops. Okay. Why am I doing something weird? Give me a minute. I can't understand why it's giving me something. Oh, okay. Sorry. Yeah, it's not giving me the wrong answer. It's just too subtle. Yeah, it's nothing wrong with this. Nothing wrong with this. Okay, just too subtle. So let's say. Okay, there. Okay, now watch this. Watch this. Okay. In fact, I'm gonna take this out altogether. That's not pretty. Well, it's pretty, but it's not. Okay, let's do this. Watch this. Let's say I'm going to start with 60 miles an hour. Okay, and then I speed up. So look at the yellow line. Look at the yellow line. It started at 60, but it's speeding up. By the way, this is starting at 0. This is starting 60, right? So what's happening is this thing here is equal to this, right? So if I have a distance that accumulates in a non-linear way, I get this. So this is actually a distance. The speed is increasing. He started at 60 miles an hour. In 2 hours, well, this is not realistic, but okay. In 1 hour, he starts from 60 miles an hour. In 1 hour, he keeps speeding up, and his speed reaches finally 300 miles an hour. Still not realistic, but okay. Oops. See if that's more realistic. Okay, now that's more realistic. Okay. He starts out at 60 miles an hour. He starts out at 60 miles an hour, and he's ending up at 180 miles an hour. So he's speeding up. Because he's speeding up, his accumulative speed or his average speed is not going to be 60, right? In fact, his speed is somewhere up here. So it's no wonder that he doesn't end up accumulating linearly. He doesn't just add time. He adds more and more time. So this is kind of accelerating. Okay. The point is, if you start with the yellow line, you get this line. Okay. Now I'm going to do something else for some reason. And don't ask me why. Okay. I'm just going to add something else. 7 log of t. Okay. Don't ask me why I'm doing this. Okay. The point is this here. Now it's forget about the car now. It's not going to be reasonable. What's going to happen is the yellow line is the accumulated amount of something. Okay. It's accumulated amount of something. And okay, this is accumulated amount of something. You start from here, it happens to be starting from negative, but the point is that you accumulating at this rate. So if you have something that is the result, you want to find out how fast it is changing. That is the slope. So if I measure the slope of this line, I'm going to get this. This function that I haven't told you what it is, it's called d function. That d comes from the word derivative. Okay, now let's go back to the origin, right? The original function, it happens to be that ft is equal to this. Okay. Oops. Okay, it happens to be equal to this. Okay, so you always have the slope by taking the derivative. So if I take the slope, I get the derivative. If I take at this point, okay, I'm standing here, watch this. I take this point, which is 30, divide by 0.3 or something like that. Yeah. Okay, and I start here. Let's start at 0. Hold on. Let me. Oh, sorry. Okay, if I stand here, okay, I have traveled 10 miles in 0.2 of an hour. So 10 divided by 0.2 of an hour give me, sorry, the line is not clear. I apologize. It's actually 12 miles. I traveled 12 miles in 0.2 of an hour. So at this point, I take this height divided by this length, I get 60. I go over here, I take 30 divided by 0.5, I also get 60. It doesn't matter where I do this, okay? Because I'm traveling at a constant speed, I can always take division. The point is that if this line, this orange line, is weekly, okay? And finally, let me do this. Okay, watch. See that? Okay. Who is this guy? Who is this guy? This is speed. This is the speed versus time. Okay. He's kind of like fast and slow. He's traveling between 80 miles an hour and 40 miles an hour. Okay. So this is what the speedometer reads: 80 miles an hour, 40 miles an hour, 80 miles an hour, 40 miles an hour, but it's always going forward. So notice when he's traveling at 80 miles an hour, this thing increases very sharply. When he's traveling at 40 miles an hour, it's slow a little bit. Okay, so let me make a little bit more more pronounced so you guys can see it. Okay, see his speeds fluctuate. So when he's driving at 120 miles an hour, go back to 0. 120 miles an hour, go back to 0. 120 miles an hour, go back to 0. That's like fast and stop, like, you know, driving between a gas station. Look at his distance. It goes up quickly, then it doesn't go. It goes up quickly, then it doesn't go. Okay? You will notice that at this point, what is the slope of that line? Well, the average is this divided by this. But if you zoom in, you will realize that he's actually traveling at no speed, 0 speed. So what's the slope of that line at that point? 0. Okay. Now, why am I doing this? Because I am assuming that some of you didn't even take calculus in high school. But even if you took calculus in high school, this is a baby calculation. The point is that there are 2 quantities in life you always want to know. What is the rate of change and what's the result of the rate of change? That's it. In driving a car, you can look at the rate of change by looking at the speedometer. You can say the accumulated effect by looking at where you are on a GPS. The point is that the speed at which you accumulate something, the rate at which you accumulate something, and the actual result is mathematically linked with this function, D. And that's the function that Isaac Newton invented or derived 300-400 years ago. Okay, so think of it this way. Prior to Newton, you can always think about accumulating things and the rate of accumulation. Okay, so you can accumulate distance, you can accumulate download, you can accumulate amount of money in the bank. You can do that, but you can do it on a large average. Like, you know, in 2 hours, I traveled 120, or in half an hour. The point is that at 1 minute, the car has traveled a little bit, right? So you can take division. The point is that Newton gave you the formula for doing it at the rate of change in 0 time. Okay. This is kind of like a weird thing. This is something that has never been achieved before. If you want to measure growth of your plant, of your money in your bank account, of your car, of anything in life, you have to say the slope is equal to the height divided by the width, right? How far it goes up and how wide it goes. The point is that is like saying, I'm going to take the height divided by the width. But Newton allows you to do this for the width getting smaller and smaller and smaller equal to 0. So what I'm trying to say is that, okay, f of t is equal to change in f of t over interval something t. Okay, that's what we did, right? Because big F of t is a cumulative distance, little f is a speed. So f is a change in f over interval t. Newton gives this. But instead of interval t, interval 0t. Okay, so that's like how far do you move in 0 seconds, and that becomes, instead of average, so that's average, okay, so this is before Newton, and Newton gives instantaneous rate of change. This is something that has not been achieved before. Now, why is it important? Why is it important? The reason it's important is simply what we showed you earlier. Remember, if all you have is a straight line, if all I have is a straight line, does it matter how far I take the time interval? It's exactly the same thing, right? The point is that in life, and this is where, like I told you, this is not linear anymore. The world is not doing proportional. It's accelerating, it's decelerating. Okay, so you just have to take my word for it that a lot of things in life do not change linearly. Okay, and to calculate the rate of change, when you don't want to take just a big average, you want precise rate of change. Precise rate of change. That's what Newton gave you. He gave you a way of calculating. So he named it calculus. Calculus means a machine for calculating, but it's not calculating anything. It's calculating the rate of change. Okay, so you can say calculus for rate of change shortened to calculus. And that is the essence of calculus. So by showing you this, you know, those of you who took high school calculus, it's already been laughing for the last half an hour at how easy it is. Okay, because you know the formula, right? Okay, but you don't realize that this is the innovation that changed everything. Okay, change everything. Because it's giving you a fine detailed instantaneous rate of change, it's allowing you to do calculation that incorporates situation where you don't have this linear phenomenon. Okay, and this is where I want you to get, you know, philosophical or think about it. right? Mathematics is trying to give you a way of measuring, predicting, calculating reality. You can imagine that before Newton, you can only calculate phenomenon that changes linearly. You cannot calculate anything else. You can approximate, like how far is the car driving instantaneously. You know how the speedometer does it? Well, the speedometer does it by measuring the rotation of the wheel divided by time. So the speedometer you see in your car is not calculus. Let me say that again. When you drive in your car, you see the speedometer, right? See speedometer, right? That speedometer came before Newton, because the way that calculation in the speedometer does is it measures how much the wheel rotates, apply trigonometry, the circumference or the diameter of the wheel, right? If it's rotated at this rate, it's actually moving 5 centimeters in this microsecond. It takes this distance, divide by that time. So it's doing linear calculation. It's not calculus. The speedometer in your car came before Newton. Well, not quite, but you see what I mean? Okay. That's how you cannot do anything that has instantaneous rate of change. So imagine if you want to go to something that is extremely sensitive. Now, does it matter that your car get a little bit imprecision? It doesn't, right? Because what the speedometer going to do, it's just going to tell you how fast you are traveling in that millisecond. And if it's too fast, you slow down so you don't get, the police doesn't give you a fine. That's good enough, right? The error is no big deal, okay? It's no big deal. So you don't need calculus to drive a car, let's say. You don't need calculus. But if that imprecision is a difference between landing on the moon and hitting the Indian Ocean 5 minutes after, 2 seconds after, 5 minutes after launch, okay? You could not launch a man to the moon without calculus, okay? Now you take for granted. So it sounds a little bit silly, right? Why do you need that kind of precision? Everything that your life is operating on is calculated on calculus. Your GPS, I really don't care. Your account, the amount of money you have in your bank, right? Everything, the game, even the game I was telling you earlier, right? There's something in there that's based on calculus as well. So it's not just manipulating screen, okay? So everything, all the things in life is possible because you have that kind of precision, that rate of change. So instead of thinking, and now I'm speaking again, for the last half an hour, I have not been speaking to people who took calculus in high school, although, you know, this is also something that you should think about philosophically. I'm talking about to people who haven't thought about calculus and think it's something that you don't want to learn. Everything in life, the minute you have time into it, you have change. The minute you have life, you have time. The minute you have reality, you have time. The minute you have time, you have change. The minute you have change, you have result of change. And there's always a balance between rate of change and the result of change. So it doesn't matter where you are. If you're an engineer, it's very important because you're responsible for launching a rocket. But if you're not an engineer, you're also responsible for a lot of things. Well, first of all, your money in your bank. Okay. So with that, I want you to, oh yeah, good point. Let's take a 5 minutes break and okay,ครับ. My bad. Okay,ครับ. So this is a picture. You know, I'm drawing this by hand, so it's not very pretty. But if you think about it, if this is my speed, okay, if this is my distance, okay, I can go backward as well, right? if I'm traveling on a straight line, my distance can increase and decrease. Let's say I'm over here at this time and over there at that time. What's my average speed? That is a straight line, right? I just take this point and take how big that is and divide by this, right? Okay. So what if I want a smaller, interval? Okay. That would mean that this line here has to be very tiny, right? You almost cannot see it. This is what I mean by calculus giving you the instantaneous slope. So if I can give you the average slope, that's easy, okay? But I want this slope. I want the slope of this line. This is called instantaneous or tangential slope, okay? And this is basically how far it goes up. Vertical distance divided by horizontal distance as the horizontal distance going to 0. Okay, let me say again. Okay, let me say again. The definition of instantaneous slope, let's zoom in a little bit. Okay, if I zoom in, it's a little bit like this, right? I'm taking this distance. So you notice that this is a cruder approximation, right? I take this height and divide by that height. Okay, and if I want something more instantaneous, I take this height, divide by that height. At some point, if I'm going to make this smaller and smaller and smaller and smaller and smaller in the limit, I'm going to be dividing 0 by 0. Okay? The point is that even though the top or denominator is 0, the bottom, the numerator is 0, the denominator is 0, the ratio is not. That's how, well, I wouldn't say fancy, but how important it is. You're actually dividing 0 by 0, except the ratio is not 0. Okay, so mechanically, how's this done? How's this possible? So think of this as y, this is x, right? So think of y and x. Okay, now, okay, so let's say I have this function, y, let me write that in text. Okay, y is equal to some function of x. Okay, now if I know that y is equal to mx plus b, I know that slope of y versus x at all time is what? Anybody? M, right? Now, I'm going to give you something more difficult. What if y is equal to x to the power 4? Okay? Okay, let's do that. Let's say x to the power 4. What is slope? Okay, of y versus x. Now, look at this picture. This is not going to be the same, right? It depends on at which point. So I have to specify at some point. So let's say at x is equal to 7.7, 7.5. Okay, that's what I want. I'm asking you a question. Okay, how do I do this? Anybody? Anybody? Well, let's think of the odometer in your car. What is it doing? It's actually moving x a little bit. So let's say at x is equal to 7.5. Okay, so at x is equal to 0.5, it's x is equal to 7.5. What's y? 7.5. Okay, now I want numerical, right? Okay, so this is the number, right? This is the number. Now, what happened if I want the slope of this function at around x point 7.5? what I can do is this. I can move x a little bit. Let's move x by 0.0001. Can I do that? Can I do that? Okay. If I did this, okay, if I did this, okay, and take y again. So now I have y initial to this, okay, y initial is equal to this. Y move is equal to 7.5001 to the power 4. Okay. What is the slope? As an approximation, again, this is an approximation. I'm doing exactly the same thing as your odometer is doing with your tire. It's moving just a tiny bit. So x could be something like a microsecond. Okay. Yeah. Right. So if y is equal to linear, I know it's m at all time. But this is, I'm giving you a specific question. Y is equal to x equal to 4. What is the slope? What's the slope at that point? Okay, what's the slope at x is equal to 0.5? Well, let's move x by 0.001, i.e. to 7.5001, and calculate y. Compute, calculate y. Okay, so if original x is 7.5, I move it just a tad, I get y move. What is the approximation of the slope? Anybody? It's very easy, right? I take y move minus y initial, okay, the whole thing, oops, okay, the whole thing divide by 0.0001. Okay, watch. Okay, that is my slope. You guys see that? You guys see that? This is so the y to the power 4 is going to be something very sharp. Okay, something very sharp like this. Okay, so let's look at something like plot. Okay, let's do this. Let's actually do this. Plot x to the power 4 from x equal to 7.4 to 7.6. Okay, it's very sharp. It's very sharp. Okay, I want the slope here. I want the slope here. What is my approximation? I'm going to take the value here at 7.5. I'm going to move it by 0.001. This is my value. Move it by 0.001 and divide by how much I move. Does that make sense? Anybody agree with, yeah? Can you see why I'm doing this, right? Okay, let's zoom out a little bit. Let's, I'm going to plot from here. Okay, can you see that? Now, if I want to take an average, okay, this is a function. This is my function, x to the power 4. If I want to know the slope from here to here, I can just take the height, divide by the width, right? But I want at this point. I want at this point. Okay, I don't want at anywhere else. So how am I going to do it? I'm going to zoom in. Okay, once I zoom in, you realize it looks like a linear function. Isn't that clever? Right? The point is, what is the slope at this point? So I'm going to approximate this with the slope of a line that passed from this point to that point. So I'm going to zoom this in. So at 7.5, I get this value. At 7.5001, I move just 1 pixel to the right and I get a new value. So what I'm going to do is I'm going to take this new value of y, subtract the old value of y, divide by how much I move. Okay. So this here is my height. So that is the slope. So zooming back in again, if this is this is my spaceship. Okay. So start from 0 miles an hour to 100,000 miles an hour. At 7.5 hours, I'm traveling at this speed. I want to know what that speed is. So what am I doing? I just take the y value at x and the new y value, right? So if instead of having this, I say y is equal to f of x. So that's my general formula, right? So I have f, if y is equal to f of x, I'm going to do this in general form now, okay? Y is equal to x, okay? What do I want? Slope of f of x at x is equal to, let's call it a. Okay. What's that going to be? That's going to be approximately, okay, f of a plus minus f of a, the whole thing divided by, right? Isn't that what I did? Right? I moved the car just a fraction of a millisecond. I see how far it goes. I divide by the fraction of a second. I get nearly instantaneous speed. Okay. What Newton does is that, okay, think of it this way. If I did this, I'm going to get very poor approximation. Okay. Which approximation do you think is better, this or this? Come on, common sense. Which is a better approximation? It's the second one, right? Okay. Which is better approximation, this one or this one? Right? Which one is better? It's going to be the bottom one, right? So what Newton did, define this as delta. Delta means change. And take the limit as delta goes to 0. Go to 0. Okay. That's what Newton did. That's very clever. Okay. How would you do it? Well, I'm going to show you exactly how he did it. Okay. Well, not in his notation, obviously. So I'm going to assume that f of x is equal to x to the power n. Okay, some number, some integer number. Okay, I'm not going to do it in the general case. I'm just going to do it in this. This is general enough. So this is what my game plan is. So what's my game plan, guys? What's my game plan? What's my game plan? Okay, again, let me repeat the question. Okay, let me write it over here. Oops. Okay. If y is equal to f of x is equal to x to the power n, okay, for some integer n, okay, see n equal to 1 or 2 or 3 or whatever, Okay. That's my question. What is the slope of f of x at x is equal to a? Okay. Now, what I'm going to do is because I'm just going to use x, so I just say at any x. It's even more general. Okay. So now a doesn't have to be 7.5. It could be any value. Okay. So game plan. This is my game plan. Okay. My game plan. Take f of x plus tiny minus f of x, and the whole thing divided by tiny. Okay, this is my plan. Okay, and then game plan, step number 1, and then step 2, see if I can make tiny goes to 0. Okay, now first of all, would you agree that's a good plan? It may look impossible right now, but that's the game plan, right? Because I want to know the speed of a car. Instead of having it drive for a minute, measure the distance, divide by 1 minute. That's a bad approximation. So I let it travel by 10 seconds, divide by 10 seconds. That's still pretty good approximation. But wouldn't it be better if I just let the car drive for half a second, divide by half a second? That's even better, right? Well, that's exactly what I'm doing. Except instead of saying 1 minute, 10 minutes, half a second, a fifth of a second, I call this fraction of a second, I call it tiny. Okay, or delta. Delta means it's a Greek word. It's a Greek alphabet. It's like a D. Okay, it stands for change. I'll tell you why later. Okay, or 1 actually. So let's see if I can make this. This is the game plan. It's actually a 2-step game plan. It's guaranteed to work wherever you can do it. Okay, except Newton did this for a general class of function. Okay, I'm just going to show you for this class of function. So what is step number 1? Instead of f of x plus tiny, that's equal to what? That's x plus tiny to the power n, right? Right? And instead of x here, I make it x to the power n, right? Okay, and that's what I'm going to do. Now, Newton did this for any number of n. I'm going to do it for n equal to 5, just to show you guys. Okay, so you agree with, first of all, you have to agree with my plan. My plan is to find instantaneous rate of change by making the division smaller and smaller and smaller. Okay, I'm going to do it for any function, but it's a little bit too abstract. So I'm just going to do it for x to the power n. And I'm going to do it, and this is going to stay in your head, x to the power 5. Okay, I can do x to the power 3, something that would be small number. Okay, so n is equal to 5. N is equal to 5. So I'm going to do exactly this speed now. So n is equal to 5. Oops. Okay. Okay, n is equal to 5. So what do I want to do? I want x plus tiny. Now, tiny, I'm going to use the word delta because that's, okay, tiny, or better yet, okay. Now, this is a Greek delta. This just happened to be Greek letter. This is a capital letter D. Okay, that's all it is. That's all it is. It's capital letter D. So what I'm going to do is I'm going to do this. Take a bracket around it. You can type this, right? Escape, escape, and capital is big D, E-L-T-A, escape. Okay, so this thing the whole thing, control upper arrow 5. Okay, control upper arrow 5, right? Okay, can you do that? Well, get this. Doesn't look very nice, right? Well, it looks nice, but so expand it. Now, anybody remember front, back, front rule, right? What's a plus b square? A plus b to the power 2. Okay, expand this. Right? This is front, right? Back, front, back, front, right? You remember that? Okay, so let's do it 3 times. Right? So this is front, yeah. This is back. This is front, back, right? Front, back, front, and back, front. The 3 of them, so you get number 3. Right? This is front, back. Okay, back, front, back, front. The 3 of them. Right? Okay. So instead of having this, I make it delta. Right? Right? Instead of making 3 times, I do it 5 times. Right? You guys know what a binomial theorem is? It gives you this coefficient when you take 2 terms and you take power. If I take any 2 terms, I call it A and B. Let's go back to A and B. And I take it to the power 5. What's going to happen, guys? Imagine in your head. There's going to be one term that has A 5 times, right? So that's this. There's going to be one term that has B. That's this, right? And there's going to be one term that's B. And there's another term called B, A, B. B. How many terms is that? 5. So if I put in N over here, okay, what is the number you expect to see here? N. Okay. A plus B multiply, right? 50 times. A plus B times to the power 50. That's what you get. See? There's one term that has A 50 times, right? There's also one term that has B 50 times, right? And then there's a term that has A and 49B. Follow, okay? You have how many combination of this? You have 50 of them. Just remember that, okay? So anytime I say A plus B to the power N, it's gonna equal to A to the N plus 50 or plus N and then this. So remember this pattern, okay? This is the pattern that was used, okay? So let's do this. So I expand this, okay? Now, what exactly do I want again? I don't want this. I want this. And I want to subtract, right? X to the power 5. Okay? Now, if I have this as x to the power, if I subtract x to the power 5, what's going to happen, guys? Well, let me Okay, let me write. Okay, I can do it here. Okay. Now, this is, do you guys agree, first of all, that this is my game plan? My game plan is I want the slope of the function x to the power 5 at any point x. So I move x a little bit, evaluate it. I evaluate at the original point, and I divide by how much I moved. That's the game plan, right? You agree with me, okay? Take a tiny step, take to the power n minus the original, divide by tiny, except instead of tiny, I write the word delta. I can do that, right? And makes delta. Okay, let's do step 1 together. Let's do step 1 together. Okay, so this is my step 1, right? Well, you know that this bit is equal to this bit, right? Yeah? Agree? Just nod your head so I can go on, speed things up a little bit. I minus x to the 5th. So I subtract this thing. So I end up with just this. Right? Now I divide by delta. So I'm going to cancel out one of them. Right? So I take one out. So I'm going to get up something like this. This minus x5. Okay. Right? Divide by this. So I take this out. So to the power 2 becomes to the power 1. To the power 3 becomes the power 2. To the power 4 becomes over 3. And 4. Okay. You guys agree that I've done this? I haven't done anything sneaky, right? This is straightforward, right? Now this is step 1. What's a step 2? Let's see if I can make delta go to 0. Because originally delta was in the bottom, I can't divide things by 0. Yeah, that's only rule in life. You can't divide things by 0. But now that this thing is not in the division, I can make this go to 0, right? Can I? Right? So rule in life, this is my game plan. Okay. So I'm going to put in the bracket, can always make delta go to 0 as long as delta is not the divisor, right? That's only game, right? Right? That's it. So these are the 3 steps. These are the 3 steps. I'm going to apply these 3 steps to this function, and I'm going to, ask you to believe me that it works for other function. Okay. So in this case, I will show you 5, but it could work for anything. So x plus something to the power 5 is going to equal to this minus x to the power 5. I get just this. I don't have x to the 5th, and I divide. So I get this. See? Exactly what I told you. Okay. Now I can take this, and this is actually Mathematica symbolic limit. Okay. Take the limit. See? Limit. Okay. Sorry. Yeah. Up. No difference. No difference. But traditionally, we use a big delta here. I'll show you where little delta comes in later. The reason I use big delta here is because I use little delta elsewhere. This is just convention. Okay. By the way, you always see this symbol in like a modern, I don't know, fintech. Whenever they want to communicate chain, they write this triangle, right? It's the same thing. That signifies change by a tiny bit. So I do this, okay? And I take this to be 0. So I end up with this. Right? Right? So I do this and I take replace. And this is just a rule, by the way. I'm just gonna. Oops. Replace. Let me look. That should be right. I don't know why. This should come out okay, actually. I don't know why. Huh? Okay, I got this. I don't know why it doesn't work. Hold on. No, that's no good. Okay. I have to work. It's doable. The point is, it's exactly what, yeah, okay. This is how I did it. Sorry. So the replace is this function. I just used the wrong function. Okay, fine. So n is equal to 5. Okay, I take the expand. Well, I'm going to follow. I prepared the note for this. Okay, and then I forgot to simplify. Okay, if I didn't simplify, okay, Mathematica is a little bit sometimes cautious. Unless you tell it to simplify, it's not going to do the simplification. Okay, so I do this, I get this. Now I want to simplify it. Okay, now see, except the bottom here, I use delta x. I can just use this. It's okay. So let's simplify. Let's do what I did just now. Okay, let's do what I did. Except I call in most math notebook, it's called delta x, but I just wanted. Okay, so you guys agree with me, right? This is n is equal to 5. Okay, I want to expand this, subtract this, divide by this, and simplify. So I get this. Okay, then I replace. Okay, with delta goes to 0. Sorry, not the word replace. It's like this. There. Okay, I used the wrong replace. It's this function. I'll tell you later. Okay. Now, come again. What did Newton do? Newton wanted precise rate of change of anything. Because he wants to be so precise, he can calculate the movement of the moon and the sun. Okay? And you should agree. Take my word for it. Your modern life doesn't matter. Building, none of this exists if you didn't have that level of precision. Okay? You would not be able to build a building beyond three stories if you don't have that kind of precision. So let's just say that because of Newton allows you to have this kind of rate of change calculation very precisely. And how's that done? That's done by doing this approximation, but in a very clever way. So take the original value, move it a little bit, divide by how much time the difference is, right? So in this case, I'm just going to show you in terms of x to the power n. Expand to the power n, subtract x to the n, original thing, divide by the tiny thing, and set this equal to 0. If n is equal to 5, you will get this. Now, what if n is equal to 79? What do you think you're going to get? Anybody? You're going to have 79 over here, right? So what's going to happen? You're going to have x to the 79, and then you're going to have 79 of x to the 78 times tiny, right? And x to the 29 will get removed. And then 79 x to the 28 tiny will have tiny cancel out. So you're going to get 79 x to the 78. So let's see what happens. See if we get this. See? This actually works for every integer number n. Okay. Now, what I'm going to show you is that this whole process is what Newton discovered, and he calls this function take the derivative. Okay, derives the slope. So this is called derivative of x to the n with respect to n. Okay, x to the 79. See, you see that little delta, it comes in, never mind. Oh, see, exact same thing. So I can put in any n, I get this. So let's say n is equal to 1,000, 1, 2, 3, 4. Okay, see if I get the same thing. Yep, it's going to equal to 1,000. So that's why you get this derivative of x to the n is always going to be nx to the power n minus 1. So that becomes a formula that works in the general case. Okay, that becomes a formula that works in a general case. Okay, sorry, I kind of ran over time, but you can see that this is what Newton did. Okay, now it turns out, and this is very important. If I put this 1 point, instead of putting a whole number, I put an, it's not going to work anymore. Okay, if I put 1.2, it's not going to work anymore. It's gonna fail. Okay, it's gonna fail because you can't take to the power 1.2. But interestingly, this formula still works because that's equal to 1.2 times x to the 1.2 subtract to 1. Okay, so even though today I just want you to be honest, no high school, I've been to high school as well, calculus ever goes through this level of detail. The reason they don't need to do that is because as long as you know the formula to do the derivative, okay, that's the most practical part. I'm telling you, you don't need to know the formula. In a way, you have Mathematica, you can do it. Just like you have a calculator, you can do it. I want to show you the nitty-gritty because I want to show you that there's no mystery. Okay? Now, the mystery is revealed in the case of the slope of x to the power n. The mystery is not revealed for the power that's non-integer. Okay? The mystery is not revealed for the negative power. Okay, the mystery is not revealed, but it does work because you take minus 5x to the minus 6. Okay, so I haven't revealed all the mystery, but by going through this horrendous explanation, taking things apart, hopefully you can see why the formulation is derived and it works. There's no mystery to it. You don't need to know anything very fancy. All you need to know is, number one, you can multiply a plus b to any power, just doing the front, back, front rule. Number two, You clear things out as much as possible. Number 3, you can't put things, you can't remove delta if it's in the bottom. You can't make things at the bottom go to 0. But once you clear it, there are some term that doesn't contain it, and there's some term that contains it, but it's not in the bottom. You can remove it. So these are the most simple rule that actually the point is everything I did today, with the exception of explanation, could have been done in 5th grade, right? Right? Because in your 5th grade, you can do that, right? A plus B, front, back, front, back. You can do it 5 times. It takes a long time. Yeah, we can do it 5 times, right? You can do it 10 times. It takes a long time. You can do it 10 times. You can divide by delta. You can do that. You can see, hey, which one is at the bottom? Whenever it's at the bottom, you can't do anything. But you notice that it's at the top, so you can eliminate it. Okay? So this here for n is equal to, let's say, 10. You can do this in 5th grade, in theory. Okay? Clearly. And then you can simplify. Right? So a 5th grader can tell you that the slope of x to the power 10 is equal to 10x to the power 9. Okay, then becomes a leap of faith that doesn't have to be 10, can be any n, can be even negative n, can be even fractional n is equal to 1.23. Okay, that's the magic that I haven't reviewed today. But this magic here that I reviewed today is literally 5th grade. Okay, why do I pick that point in time? Because 5th grade was a couple of years before you have to separate into art and science track in high school, basically calculus and non-calculus. I know that because I have a girl. So in high school you have to separate into calculus and no calculus. I think in your 10th grade or something like that, right? Yeah. Some schools start calculus early. So anyway, 5th grade is a safe spot. So this requires nothing more than 5th grade mathematics to show you. But this is so powerful. It allows Newton to calculate the orbit of the moon, the sun, and the star, and allows you or NASA to send a man on the moon. Allows you to have building that's calculated, because if you think about it, a building has to carry your weight, right? The building has to carry your weight. The building itself is weight. The concrete is heavy, okay? As you add more concrete, what do you add? Load. So you have relationship between the rate of accumulation and the result. So as you're building 3rd floor, 4th floor, 5th floor, you have to know that you're adding more concrete. It carries more load, but it's also heavier, right? So if you don't have calculus, you probably have to have something that's overbuilt, like a pyramid. Yeah, a pyramid, you can do that because it's actually just blocks of stones, okay? But you can't have like skyscraper with, a lot of open air. That's just impossible. So there's no wonder why the ancient civilization, given enough manual labor, can build pyramids. And forget about aliens teaching Egyptian how to build pyramids. Everybody on earth built pyramid this shape, okay? In South America, the Incas, the Mayans, the Egyptian, they all built this shape because they can't build this shape, okay? Because they have no calculus, basically, okay? How do you minimize the material that adds load? It requires calculus. Okay, so with that, I think hopefully when we go to Wednesday, now this is what's going to happen on Wednesday. On Wednesday, we're actually going to do quote unquote calculus as if you were doing in high school. I wouldn't be motivating you guys with this 5th grade mathematics anymore. Okay, but hopefully you bought the story that I'm trying to tell you today. Okay, you need this, you need this, you need this. Wherever you have time, you have change. Whenever you have change, you want to calculate the rate of change. Okay. And instead of having time, the dimension could be space, and that's the building you're living in. Add space, add floor, add concrete, it gets heavier, and so forth. So everything in your modern life is made possible by calculus. Okay, calculus. And for you who are not going into, for you who are going into the applied digital intelligence, you will see calculus a lot more because you need to do that in machine learning and whatnot. But for those of you who go into other tracks, you will also have calculus. For example, I told you last week, and this is the last comment I'm going to make today, the spread of COVID is predicted by calculus. It's the rate of change of infection and the resulting accumulation of infection, right? So the same equation that governs the epidemic is written in calculus, literally in calculus. Okay, so you guys going to see that a lot. The point is that with Mathematica, you have this function D, and the last thing I will show you is just this picture. Let's say you were given, and this is what I mean by in application. Let's say for some weird reason, you work in biomedical technology area, or you work in nanorobotics, I don't care. And you have this quantity that relates the change. You can plug this in Mathematica. Okay, so this is a function. This is the derivative. And so I can plot the function and its derivative, right? So this is a function. This is its slope. Okay, so the blue comes first. Blue is this line. I can make it. I can make it any kind of weird function. So let's say you go into some problem and you have that, right? You can literally do this. Okay. See? Oops, it's a bit hard. Well, take my word for it. It can be any complicated function. Okay. Okay. So you can run into any complicated function and take it through. Okay.